Hello. Yeah, good evening, everyone. So, uh, so this is our week 2 of NLP class. So, sorry for being late. Yeah, so we will be starting within a few moments. Yeah, just give me a second. Okay, so welcome to the week 2 of this lecture. So, I am Shubhanu Haldar. So, I am a PhD student at IIT Delhi. So, so today will be like as discussed in the earlier weeks also, like in the first week we have seen the many large language models, and we just got introduced with those language models. Okay, so I promise that in every week, so as this is a course of natural language processing, so here you get to know the theory of the natural language. What are the theories behind it? This is not a large language model. This is a so in this topic, in this course, you are basically acquainted with the how the language models work. So mainly, we will be seeing the probabilistic model. So today in this lecture, we'll be seeing in the n-grams models, the unigram, bigram, and trigram model. What are the techniques for this? Yes, yes, please, yes, please go ahead. Yeah. Lot of taking voices. Yeah, that's I am trying to do. Hmm. That is because of some servers in our lab. So yes, like last week I took the class from my room, but today for the time constant I didn't move to my room. So this noise is coming because of the server from the servers only. I think you have to go with it only. So I am trying my best to speak it loud so that it is audible for you. Okay, fine. I don't think that there is a much noise. Hmm, hmm. So can you hear me clearly? Okay, go ahead. So So last week we have seen some of the LLM models, like what are the recent advancement in the research in these models. So congratulations all of you that this week we have come with a new model. I think most of you are aware about this that is DeepSeek. DeepSeek. So it is implemented from the Chinese community. I was in the Google's office last week in Bangalore. So when this DeepSeek model came up, so I was also talking with some of the researchers there who was active participant in the building of the Gemini, which is the Google's official LLM model. So yes, like as a researcher, you have to be aware about this kind of thing, that what is coming. So what are the things they are using to building such models? So the main difference, I know that most of you are aware from the internet and all, but let me reshare this that the DeepSeek model, they are using some reinforcement learning in their training, and that training was very fast, and they can do the inference with a very less amount of money. Okay, so the cost behind this large language model is has been reduced by like 30-40%. So that time, as the NVIDIA GPU was used by these large language models, now OpenAI use this NVIDIA GPU, and like many of the most of the companies is using their the NVIDIA GPU. So the share prices of the NVIDIA GPU also go way down. So they lost about 435 billions of rupees, a billion, sorry, dollars. Yeah. So this is the latest update in our this LLM era for natural language processing. So as you are a student, so this is important to know. Okay, so as so our class is structured in this way. So this tutorial, so we will be trying to solve some questions. So behind that, I will be giving you the recap of the theory. So uh, the main motivation of this class to solve the questions only from the previous assignment and all. So it is required that you from your yeah Nobin, you will say, just give me a moment. Yeah. So it is required for all of you that you go back and see the video lectures from the Professor Pavan Goel's lectures. Okay. So it is very important that you see those lectures and come in the class so that you can solve the questions and all. Okay. So this is one requirement. So and another thing I'd like to mention that yes, there are two things. One is we are looking into the NLP, and we are also looking into the LLM. So this is our course, NLP. LLM is not our course. But to learn the LLMs, we have to first cover some of the topics in the NLP. Okay. So first day I have tried to introduce some concept of from the LLMs, like what are the models I introduced you. So this week I feel that some of the topics is important, very important. So this is the chapter 3 of the Jurassic Martin's book. Okay. And this chapter is important to understand the probabilistic modeling for probabilistic modeling in the scope of NLPs and all. So we use probabilistic modeling to uh, for different purposes, like predicting next word, or like so in Google you type something, and you predict. So Google give you some possible solution to your next word you are going to type. Okay. So how this is happens? So previously that probabilistic model was used, and now LLMs has covered this, and you can see there is a Gemini output after when you type in the Google Chrome, you are searching for something. then Gemini will give you suggestion. After that, you can find some web pages there. So this is happening in the scope of so LLMs are being used like this. So today's week I will not be covering much new topic because this topic covered in today's lecture by Professor Pawan Goel is very important to know the probabilistic modeling, and also I will add something. I'll add something on top of that only. Okay. So this is how today's lecture will be uh, going on. Okay. Okay. So some of you have some questions. So Naveen Kumar has raised your hand. So can you please turn on your mic and tell me what's happening? Yeah. So do you have any query, Naveen Kumar? Okay, fine. Okay, great. So last week also we have seen this Jeeves law. So according to Jeeves law, let's try to solve some question. So this is the first question of today's class. So as we will go ahead, so we'll be seeing more complex questions. So there our theory will come up. So let's warm up and try to start from these questions. That according to Gibbs law, which statement is correct or in between these two statements? Yeah. So you can write your answer in the chat box. You can please write the answer what you think in the chat box. Yeah. So there are 40-45 people are joining the board. So yeah, thanks Shruti for giving your response. Mm. So anyone from you can remind me about the Jeeves law. So if anyone remember what was it that which was so I can remind you. So A proportional to 1/r. So can anyone? So Pradeep, you are giving you're saying that option is the right option is option A. So Pradeep, can you turn on your mic and tell me that what was the Jeeves law? What was it saying, and why you are saying that it is option A? So you can turn on your microphone and tell me. So whatever you think, you can tell me. So I think many of you have given the answer. Like Kruti, you can also tell me like why do you think that option A is the correct? Okay, okay. So fine. So yes, option A is correct. So so we have seen in the last week that in Jeeves law we count the frequency of each word type. Then we list the word type in decreasing order of their frequency, and that's how we find that if the frequency was proportional to 1 by r, which is the rank of the in the decreasing order. Okay, so in Gibbs law, if you imagine you have a huge text like if you collect word from all the books ever written. Okay, so that's a huge number of text. Okay, so if you list every word in that text from most frequent to least frequent, you will find a pattern in those words. Okay, so that's why from there Jeeves law came into the picture. That the most common word is the. The in the English, in every sentence you can find that. Here is also like maybe you can find there is the. So so that is the very common word there. So it appears very often. Okay. So the second most common word is of, and the third most is and. So this is how so that's why Gibbs law says that F is proportional to 1 by R. Okay. So now there is another concept of Gibbs law, that was M was proportional to root over of F. Okay. So M means meaning of a word. Okay. Fine. So from there, we have seen that a small number of words occur with high frequency. Okay. So, and a large number of words occur with low frequency. Okay. So this we can conclude from this formula. So the both option is right. Okay. Now come to our second question, that is consider the following corpus C1 of four sentences. What is the total count of unique bigram for which the likelihood will be estimated? Assume we do not perform any pre-processing. So this is the basically this is the four word which are uh yeah. So today is Sneha's birthday. She likes ice cream. She is also fond of cream cake. We will celebrate her birthday with ice cream cake. Okay. So this is a corpus of four sentences. Okay. So these four sentences, there are four sentences. If we So these four sentences together makes a corpus. Okay. Now, what is the total count of unique bigram? So what we have to count? We have to count the unique bigram. Okay, number of unique bigram. So can you count the unique bigram? So for which the likelihood will be estimated. Okay, so this is the thing. So how will you calculate the unique bigram? So that's the question here. Okay, so you have four sentences. So as you have the four sentences, so if you know how to solve, then you know. If you don't know, so I am trying to give you an idea so that you can do this exercise and tell me. So how can we count a unique bigram? Okay, so unique by so at beginning of every sentence we add a starting sign, and also at the end we give a this ending sign. Okay, so this is like that, and yeah, this is the starting, this is the ending. Okay, so you have to also count this ending and beginning and ending statement to count the all the unique bigram. Fine. So can you work it out and tell me the answer in the chat box? So I think you have all seen those lecture videos from Professor Poyangog. So this is important. Okay, so but I'll remember you that first what we have to do. What is the first step? So you will list all bigrams. Okay. So what is a bigram? So bigram is a sequence of two adjacent words. Okay. Sequence of two adjacent words. Oh, I'm sorry. Yeah. So what we have to do, that we have to, what is the steps to solve this question? That we have to find all the unique bigram for which the likelihood will be estimated. Okay. So we have to find, so here the question is, what are the unique number of unique bigrams? So we have to find first that what are the all bigrams. So if we can find the all bigrams, then from there we can list it out that what is among all of that, what are the uniques. So how can we find a bigram? So what is a bigram basically? So bigram is a sequence of two adjacent words. Okay. So like this is today. So this is also, you have to take this also as starting of a sentence, also as a word. Okay, because this is the starting of the sentence. So these two makes the bigram. Okay, then what happens? Then today is, these two is a second bigram. So this is bigram one. This is bigram two. Then is Sneha. Is Sneha is also a bigram. Okay, B3. So like this you have to play around, and from all of these four sentences you have to find the number of unique bigram. Okay, so can you please work on this and tell me that how many numbers of unique bigrams are there? Yes, please. Yes, please. Mm-hmm, mm-hmm, mm-hmm. Yes, you have to add the sentence beginning and sentence end character. No. We have to, yes, we have not done any preprocessing, but we have to add these beginning and ending characters. Mhm, mhm. Thanks, Asha, for answering. So you are saying 28. Yeah, we'll see. We'll see what the answer is. But are you counting all the unique ones? So can you work it out more? So I don't think this answer is correct. So you can think of changing your answer. So you have time. So you can work out a little bit more to see. Uh, yeah. So this is a request to everyone that you can write your answer in the chat box. Let's see. Hmm. So I think you have given the answer. Yeah. So let's try it out. Yeah. So I have also tried to write it down in this manner. So, hmm. So my findings were like this. So this is S today, one. So then is Sneha's birthday is. Okay, like this. Sea legs, ice cream, cream ice. She is also fond of cream. If S will celebrate her birthday with ice cream cake. Yeah. So here we have five, five, four. So my solution was it should be 24. Okay. So thanks all for answering. Yeah. So let's try to do solve this question. Yeah, this is a easy one. So this is from the theory only what we have learned from today's lecture. Okay, okay, fine. Uh, yeah, so I am trying to give you a idea of this Markov model that why this came into the picture. So yes, the answer is very simple that the Markov assumption using the Markov assumption that the answer is two. So everyone knows this. So there is nothing new into it. So I hope you all know what is the Markov assumption says. Okay. So so Markov assumption. So is there anyone who doesn't know what Markov assumption says, or anyone can unmute yourself and say that what is a Markov in Markov model? So I am just curious about the Markov assumptions. Okay, not the Markov model. Yeah. Yeah, exactly. So thanks, Dibbo Banerjee. Yeah, thanks for answering. So at least this introduction is required. Yeah. So the interesting thing is that why this came at all. Okay. So I'll take a pause here to I'll recall some theory here. Then we'll go ahead. Okay. So why this came that this assumption why this came that we know this theory is important. So in our language landscape, so we want to try to predict the next word. Okay. So how can we predict? Okay. So suppose I want to say that I am saying that my what is my previous word? So I like uh, pizzas with loads of something. Okay. So this is my previous word. Okay. That I like pizza with loads of what? Okay. So what can be here? So it can be cheese, it can be corn, it can be tree. Okay. Or it can be chicken. So suppose you have three options to choose the next word of. Okay. So which word will be predict? Okay. So this is the previous word. Okay. So so you can. predict cheese, you can predict corn, or you can predict tree. Okay. So the thing is, this is written like this, that probability of choosing cheese given I like pizza with lots. Okay, so this is the kind of thing. Now you can see that the probability of choosing this cheese is greater than probability of predicting corn. Then and this the same sentence is given here. Okay, and this is also greater than probability of predicting tree when given the same sentence. Okay, so this in this dashed line, I am saying that these sentences will be here replaced by here. So here this probabilistic language model came into the picture, that these probabilistic language models can be used to determine the most plausible sentence by assigning a probability to a sentence. Okay, so it can be used in your speech recognition, in your or in your machine translation. That machine translation means so you can say that a probability of heavy rainfall is much given that probability of big rainfall. Okay, so heavy means also kind of it also kind of big. Okay, so this is kind of thing. Okay, now also you can use it as natural language generation or context sensitive spelling correction. Okay, so also in if you open the Google Chrome, like Google Chrome, and want to see and give some translation work to Google, that from English to Hindi and English to Bengali or English to Marathi, like that. So it can do the language translation. So so let me tell you a story. So now the game is changed. Okay, you can, if you type in Google, if you type in the Google that translate me something, translate for me from English to Hindi, it can do it. It can easily do it, because this Hindi and English both are very this language is told by many of the speaker. The speaker range is very huge there. So uh, so uh, uh, la- uh, so in Google, what they are doing now, uh, they are trying to so there are some language from the Adivasi community. Okay, so one language is called Bhili language. So there is no corpus. You can't find any corpus of this Bhili language. Then how one can convert this English to Bhili or Bhili to English? Okay, so this Bhili language you can find in some places of Madhya Pradesh and Rajasthan. So anyone from in this audience speak Bhili or know what Bhili is? So I can tell you that the Google is now trying to, what they are doing, that the Google engineers are going to places, that Bhili places. They are now collecting the same data from everyone. They are collecting a voice note. They are showing you a sentence. Okay, so uh, so they have collected some school teachers. Okay, so they are showing them a sentence. They are saying them to just say the sentence, whatever it is written. Okay, so they are collecting uh, the text format of in Bhili language. They are also collecting the audio format of the sentence also. Okay, so that gives them, and also the handwritten thing, like also the what is it called, the text. Okay, so like one thing that you have to speak, you have to in a writing format and in a reading format. Okay, so all these are is a multimodal data. So we have seen the language models which is used for transforming from one language to another language. But now researchers are trying to focus on the multimodal models, like what they can predict the speech, they can predict the handwriting, like the how it will be written, and everything in a from a single model. Okay, so this is now how the market is evolving, the research is going. So come back to our probabilistic model. So in our probabilistic model, we want to predict a word or a sentence. So in this sentence, this sentence is consist of many words. We like this. Okay. So this is the sentence, and these are the words. Okay. So now, we have to do, we have to find out the probability of W6 if given W1 to W5. So this is the task. So this is the goal. Okay. We have to predict the sentence, and this is the task. This is the yes task. Okay. Is it clear? So now a model that calculate either of these is referred to as a language model. Okay. So, so the thing is that we in to solve this using the probabilistic model, we always use the chain rule of probability. You know that there are two things. One is the conditional probability, probability of AB, which is probability of AB given probability of B. So this is the conditional probability, and if you rewrite this, it is to be probability of A given B. So this is called given probability of A given B into probability of B. Okay. Now, so this can be of multivariate. Like you can do it like A, B, C, D, which will be like probability of A into probability of B given A into probability of C given A, B, like this into probability of D given A, B, C. I think all of you know about this, but it's a quick recap only. Okay. Now it comes the probability of a sequence. Okay. So sequence means, yeah. So probability of a sequence. Probability of a sequence means that probability of W1 to W2 to WN. So to count this, how we do it, that probability of Wi given W1 to Wi minus 1. So this is how we calculate it. Okay. So if you want to see, like, do you anyone is not able to understand this, how it is working in our natural language scape scenario? So they can mute themselves and tell me that yes, it is not understandable. I can give you an example and tell you. Otherwise, I will go ahead. Okay. So like don't hesitate. Okay, so just tell me. I can give you an example so that you can understand better. Otherwise, I'll go ahead. Okay. So this is called probability of sequence. Then so using these, we have a problem. Okay. So in natural language processing course, you can see that you can find that yes, there are many solutions they have discussed, many algorithms they have discussed. Like in spelling correction, we have seen that edit distance this week, edit distance, then noisy channel model for spelling correction. Okay, so we have seen this, but there's a problem. So no one is talking about the problem. So what is the problem here using this conditional? If we use this conditional probability and all, okay. So the problem here is that the enough data is not available to get an uh, accurate estimate of the above quantities. Okay, so that's why we so I can give an example. So the probability of begun. So we have to predict. the word begun. Okay. So then what is given? The given word is the monsoon season has. Okay. So it can be begun, it can be started also. Okay. So how we count this probability, how we calculate this probability? So we have a large corpus where we have collected all the sentences from all the books in the world. Okay. So we count the how many time it is written that the monsoon season begun. And also we count the monsoon season as. Okay. So are you getting the point? So basically what I'm saying that this sentence is this sentence. This is same. So I am counting how many times in my corpus the monsoon season is there and how many times. So we have this monsoon season has begun is there. Okay, so that's how we count this. But the problem is that if you keep if your sentence is very long, then the data will not be available. So that's why what you do, we try to assume that there is a Markov assumption. Okay, so always we will not take a very big sentence. Okay, so we assume that the begun only depend on season has. Okay, so then this monsoon can be replaced with winter, and also winter can be replaced with summer. So that's why if we just take into account the season has, so these two word can help me to predict the begun. Okay, got it? So maybe in my corpus, the monsoon has begun is there, but the winter season has begun is not there. So that's why this can help me to predict the begun word. Okay, fine. That's why Markov assumption is there. Then and this Markov this n then we came to this n-gram model that that n-gram model considers that only the preceding n minus one word, like so if the model is n-gram, so then only preceding n minus one word, that this preceding n minus one means if we are taking a 3-gram model, then only two words, first and second. Okay, these two word we follow it for follow it as a Markov assumption. So that's how our unigram, bigram, and trigram model came into the picture. Unigram means, so what does it mean from the unigram? Unigram means, so in your corpus, so you have a large corpus of all the words from all the books. So you will just calculate the probability of begun. This is called unigram. Okay, so just you will calculate where there is a beginnings. So this is called unigram. So then bigram, what does it mean by bigram? Bigram means you will calculate the probability begun, but with the word the. So you will find the begun. So you will find your corpus where the begun is there. In diagram, what you will do? In diagram, you will find the monsoon. Right? So this is the thing. Yeah. So this is how the unigram, bigram, and trigram works. Okay. Now, mm, now, yeah. So this is this was the answer to your question. So we answer that 3-gram model is a two-order Markov model. Okay. Now there is a problem that I can show the problem with the mm, hmm. So using this diagram, what can I do? Yeah. Yeah. So using this bigram, we can calculate a bigram table from there. Okay, that is the raw bigram counts. Okay, So suppose so I want to uh, Chinese food. Okay. So here also you have I want to eat Chinese food. Okay. So you can see that suppose I am giving you just a simple example of like mm, a raw bigram model. Okay. So like you can see that this number is very big, 827. So so like every time when you say I, like so many times you say that I want to do it. Okay. So but you never say I to do it. Okay. So if sometimes you say I eat, okay, but you never say I Chinese, I food. Okay. So this is how. So this is the bigram table. So what is this? What I am drawing now? This is a raw bigram table. Okay. So basically, this number says how many times these two word appears together. Okay. Any problem? Yeah. So I never say want or want eat, want Chinese like this. Okay. So now want to the I also say many times like 648 time I say that I want to like this. So if you just use some simple intuition of your mind, you can see that these word are like practically correct. Okay, so this is like that. Okay, yes, 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 based on a particular corpus. So I am just giving you a snapshot of the corpus. Okay, nothing else. So, but in many of the corpus, you can find the similar structure there. Okay. Yeah. So this is the thing. So this is a raw bigram table. Okay. So uh, yeah. So this is how raw bigram table is generated. Okay. So I will come to this raw bigram table later because when we will be talking about the normalization and all, I will come to this. So what I have developed till now, so I was talking about the Markov assumption that how. So my goal is to predict the next one. So you are an engineer. So suppose you are working somewhere. So your company tells you to to build such a system so that you type something. So you will type I like, you will type that I like pizza, and the begun or the cheese will come. Okay. So it should not come that I like pizzas with lots of tree. Okay. So this should not come. Okay. So that's why you have to find the probability of cheese. So how you will find the probability of cheese? You have to find that in the corpus. Corpus means that there is a lot of text there. Okay. So you have collected all the books from all the from around the globe, and you have a big dictionary kind of thing. Okay. So from there you are just finding, you are just matching that thing. Okay. So this is the goal that we have to we have to find the probability of the sentence, and in the sentence we have given some words. So sentence is made of the words. So that's why we use the uh, we use the how can we find the probability? That we can find the probability by counting this, like monsoon season has and monsoon season has begun. We just add the next word which I have to predict that is a correct or not, and we append this and then find it in the corpus. So then there is a problem that if we have a big sentence, the problem is that in big sentence we really can't found the big sentence in the corpus. Okay, so that's why Markov came into picture that with his Markov assumption. So Markov assumption says that every word. So Markov assumption says that every next state depend only on the previous k state. Okay, but we don't know the what is the number of k. K can be 1, 2, 3. Okay, so in unigram means that so n-gram means each step is depend on n minus 1. So unigram means that zero step. So I have to find the probability of begun. That means you find the probability of begun only. So if this is a bigram, that means probability of begun given the. If this is a trigram, that means probability of begun given the monsoon. One word and second word. Okay, so this is how. So now what I have done, that I have written a raw bigram table. That means it says that how many times I want appears together, how many times I two appears together in my corpus. Never. So I Chinese, okay, appeared together. Never. I food, it appears never. So maybe you can see that some of the times it appeared that Chinese food, it appeared many times. Okay, yeah. So that's why it is 82. Okay, and 686 time it appeared that two it appears together. So I want is has the highest bigram count. So this is all the theory I have built. Now we'll solve another question and see that how this will help in our next theory building purpose. Okay. So yes, please. Yeah, please go ahead. Mm-hmm, 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 mm-hmm. So say so it is of week 2 or week 1? Okay. So can you just copy paste it into the chat box? I don't have access to that. Okay. Okay. We'll discuss it in the so please copy paste it. Okay. So we'll discuss it definitely. Yeah. Okay. Mm, mm-hmm, mm, mm-hmm, mm-hmm, mm, 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 mm. Okay. Acha, acha. This is a silly mistake. Uh, mm, mm. So who made this assignment? So maybe done this mistake. So he was just trying to made a similar kind of assignment and done this mistake. So this is a mistake. So yes, 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 yes. Yeah, yeah. Thanks. Yeah. Okay. So the question is now that which of these is a valid Markov assumption? Okay. So can you type your answer in the chat box? So there is multiple correct answer. Okay. This is the multiple correct like MSQ like option. Mm, we'll see it. Like, but I am saying that there is a multiple. We'll go to the correct answer. But I'm saying that we have a multiple select answer here. I don't know, but this should be three answer there. So if this is not a MSQ, then you can find it MCQ like this, which are not. So correct answer is A, C, and D. So because like so this is very easy that the probability of each word depends only on the current word, not the previous word. Ne- We it's also depend on the probability of word depends only on the next word, current word, and probability of only on the current and the previous word. Okay. So the previous word we didn't take into the account. Okay. So so only the previous word we don't take into the account. So we can take into the account the probability of word depends only on the current and the previous word. So these two we can take, but this is not the option. Mm, no, no. His diagram model will be. Mm, I think there is something wrong in this question. I think something there is wrong in this question. I don't know. Uh, yeah. Ah. Hmm. Hmm, 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 hmm. Hmm, 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 hmm. Yes, yes, yes. Word or word. Yes, yes. That according to the Markov assumption only, like it should be like every next state depends only on the previous case state. Previous. See here the word previous case state. So I don't know. I don't know. I don't know the answer. But we know the Markov assumption. Yeah, that's fine. So I am skipping this one. So like you know the answer. Like whatever the assignment is giving, we don't need to like spend time on that. Yeah. So this is the next question that for the string mesh, identify which of the following set of string have a Levenstein distance of one. Yeah, Levenstein distance we have seen in the edit distance thing that I think you all know what is the edit distance. Like you can do insert, you can do delete, or you can do what is the another thing? Insert, delete, and substitute. I think. Yeah, substitute. Yeah, yeah. So these three things we had. So for the string mesh, identify which of the following set of string have a Lavenstein distance of one. Yeah. So this thing you have to just check it out. Like, so how like I am just telling you how if I were in your position, then how should I solve this question? So you can also go ahead with me that if smash, so smash I can insert if then smash can come. In MAS, I can delete H from mesh. In LASH, I have to delete it and basically substitution should be there. Like from L, I have to substitute M. Mashi can be done because I have a one insertion operation here and I also have a substitution operation here. So Mashi will fall. So this A is not an option. Okay. So, so are you getting my point that how I am trying to solve? So Bala So you are giving the answer. So Bala, can you say your name, like how you pronounce it? Yeah, fine, no issue. Okay. So 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 A is not an answer because you have given the answer A, because you can see that we, if this Mashi come, the MUSHY, then for you have to substitute with S, and then you have to insert I. So that's why edit distance is 2. Okay. So that's yeah, no issue. So I think the correct answer is C, because smash 1, MAS 1, LASH 1, MUSH. So this is also a substitution. This is 1. ASH. So this is a one. This is also a 1. So I think C is the correct answer. Right? So yeah. So Nita, Jadov, and Asha also gave the correct answer. Yeah. Thanks all for like solving, trying to solve this. Yeah. So can you try this one also? So assume that we modify the costs incurred for operations in calculating Levenshtein distance such that both the insertion and the deletion operation incurs a cost of 1 each. So deletion and insertion. So insertion 1, deletion 1. Yeah. While substitution incurs a cost of 2. Okay. So this is the cost given. This is a kind of weighted edit distance. Now, for the string lash word, which of the following set of string will have an edit distance of 1? Yeah. So our given word is L A S H. So basically, what you have to do, you have to find among which option A, B, C, or D. So edit distance is always 1, not 2. So basically, you would should not use substitution anywhere. So can you give the answer? Yes, I think also. In a slash, oh, it's an insertion only. Hmm. Here you will fill. Hmm. In clash, no, you just insert C. So here, so you are saying that clash will also substitution, but no, so you have just insert C there. No. Mm-hmm. It's insertion. Yes. Yes. It will fill. It is two. Mm. It is also. ST, SH. So here B is a substitution. So none of the above is correct. Fine. So let's move ahead into our next thing. Uh, yeah, so we have a lot of theories to cover here. So given a corpus C2, the maximum likelihood estimator for the bigram dried berries is 0.4. So the thing in our that course is that so do everyone know that what is the maximum likelihood estimation for the bigram? So what does this mean basically? That dried berries is 0.4. What does this means? What does this statement means? And the count of occurrence of the word dried is 680. What does this means also? For the same corpus C2, the likelihood of dried barriers after applying add-on smoothing is 0.05. What is the vocabulary size of C2? So do you know the meaning of this? Know the meaning of this and why we are using add one smoothing? So if you know, then I will not teach. Uh, if you don't know, then I will try to get you some insight. Yeah. And, hmm. So yeah. So what we have done till now, like we have seen this table that that's why I built that theory that we have seen what is the raw bigram table looks like. What does it mean by raw bigram table? Raw bigram table means that you have a table where this there is a count of I want, I two, I eat, I Chinese, I food. So you have a corpus. You have a corpus meaning you have a some like all. So suppose there are English books, okay, and you have collected all the sentences from 20 20 30 or from all the English books in your computer, and you are checking with that, okay. So this is the corpus means. Okay. So corpus means basically a huge dictionary. In dictionary, we have a single word and their meaning. So a corpus is not like that. Corpus is like the word sentences, sentences, and sentences. So there are only paragraphs. Okay. So you can think about this way. Yeah. Now what we are doing? We are trying to find the raw bigram. Raw bigram means that how many times I want appears together. So I want appears together. How many times I two appears together. So this means I two appears never together. So this means I want appears 827 times. Okay. So this is called a raw bigram table. Now, what does it mean by raw unigram table? So I am saying you the raw bigram, but I am not giving you a intuition of raw unigram. What does it mean by raw unigram? Raw unigram means how many times I appeared 2533 times. Okay. In my corpus. So suppose I have a corpus. Okay. So I one appears 927 times. Two appears 2410 times. Like it appears 700 times. Okay. Chinese appears only 50 times. So like this. This is the raw unigram table. Got it? Now the thing is that uh, uh, this table is very you can see that you have a. So I am just giving you a snapshot of my corpus, but this bigram table is very big. Okay, so you have lots of sentences and you have lots of words, and if you count the bigram all of this, you can see from this small snapshot that many of the places the values are zero. So if you have a matrix, so you can see this as a matrix. Okay, so you can see this as a matrix. Okay, this forms a matrix. Okay, so in this matrix, you can see that most of the entry is zero. If most of the entries is are zeros, then you can call it a sparse matrix. Okay, okay. So if it is a sparse matrix, then there is a problem in some situations. Okay, so what are the situation that yeah now now what we do that we do something called uh, we estimate n-gram probabilities. Why do we estimate n-gram probabilities? So how do we estimate n-gram probabilities? We do it by MLE. MLE means maximum likelihood estimator. Okay. So this is used to estimate the parameter of the statistical model, and this determine the most likely values of the parameter that would make the observed data most probable. Okay. So bigram probabilities can be estimated as, so I can uh, estimate the bigram probabilities like this. Probability of Wi given the previous one. Bigram means I will only count the previous one. I have shown you with an example here that bigram means begun the. So I am just saying that, so this is begun, this is the. Okay. So now what I will do, I will calculate, how will I calculate the probability? I will calculate the count of Wi minus 1, and also I will calculate the count of Wi minus 1 and Wi. Okay. So this will give me the bigram probabilities. Okay. Now, uh, so there is a limitation in this estimation. So the n-gram only work well for word prediction if the test corpus looks like the trading corpus. So it is not often the case of the real scenarios because the data is very sparse. So you assume that, like as I was giving you this simple example, that this if your corpus has you have the corpus. Okay, now you all know the machine learning approaches. So you have a training data and you have a test data. Okay, so if the training data looks similar with the test data, then this model will work fine. Okay, so suppose you have to predict the season, and this winter is not in your trend data, then you will never predict the season word. But it is the most suitable word with any word like season, summer, or winter or monsoon. Okay, so this is like the case. Okay, now the problem is uh this like, suppose I can give you an example, like if your training set is like this, training set and your test set. Your training set is enjoyed the movie, okay, but your test set co- consists of enjoyed the concert, okay. Now enjoyed the food, but in your test set it has enjoyed the festival, okay. So if this is the scenario, like here you have movie, you have concert, food, festival. Okay. So if this is the scenario, then you will have a problem with these n-gram models. Okay. And also, these problems lead to a serious problems called zero probability n-grams. Why this is called zero probability n-gram? Because you have never seen in your training data that there is probability of concert given enjoyed the is equal to probability of festival given enjoyed the. So this is, the probability is zero because you have never seen in your training data. Okay. Now you have to find the perplexity. Okay. So I think you all have read about this thing. Okay. So perplexity is like, you have seen the theories and all. So if I, yeah, perplexity is the inverse probability of the test of the data normalized by the number of words. Okay. So Sir was written PPW, perplexity of the word is probability of W1, W2, Wn to the power minus 1 by n. Okay. So lower perplexity means better model. So so this is also a very good like so we have to this has many application, this perplexity has. Okay. So if we have this kind of situation, then the thing is that we can't calculate the perplexity. So what is the problem? Problem is we have zero at many places. What is the problem? Problem is we have zero at many places. Fine. So as this is there is zero as many places, so that's why we call this matrix as sparse matrix. Okay. So this was the problem. So then how can I remove this zero, or what can I do to remove this zero? So if this was the problem, so that's why we can't calculate the perplexity. Okay, so let me write it again. Hmm. So what was the problem? And what was the thing that basically that many places, or I can write it like that, that the bigram matrix. So I'm saying the bigram matrix is sparse. Sparse means there is many at many places there is zero. So what is the problem? Uh, Problem is can't calculate the perplexity. Okay, what we so this is the problem. What is the solution? Solution is the smoothing technique. Okay, so what do we do with yeah? What are the available smoothing techniques we have? We have the Laplace smoothing. Okay, so this is also called add one estimation. Add one estimation. Okay, what does it do? That if you imagine that we encountered each word uh, one more time than its actual occurrence. Okay. Uh, mm, so basically, what we do, uh, we here in place of zero, at every place I add one. 5 plus 1, 2 plus 1, 2 plus 1, 0 plus 1, 1 plus 1, 15 plus 1. 827 1 8 0 plus 1 0 plus 1 0 plus 1 0 plus 1 0 plus 1. Are you getting my point? So every all in whole matrix we add one. That means that you don't have any zeros, and also this is not affecting you that much. Okay, so previously how we estimated the MLE in terms of bigram. Yeah, so this was the thing, that how will I estimated the MLE. Okay, so yeah, so let me write it again. So we estimated MLE. So we estimated MLE as WI given the previous word. Okay, so it is count the number of WI minus 1 given WI and count of WI minus 1. Okay, fine. Now in this situation we have seen that we have seen the thing that we are getting many zeros, so that's why we are adding one to it. Okay, so we are adding to each at each entry we are just adding adding one. Okay, so that is called add one estimate. add one estimate. So what do we do in case of add one estimate? Probability of add one, so that is wi given wi minus 1. Okay, so this means that count of wi minus 1 comma wi plus 1 and count wi minus 1 plus plus number of p. So now we have to see that why there is plus 1. We have seen that why there is a plus 1. But can you tell me that why there is a mod p? What that is mean? What that, does it mean mod p? Like why there is a mod p? So plus 1 we have seen that we have entered plus 1 here because at each entry we are just adding 1. But why there is mod p? Like why we are adding mod p here? Can anyone tell me the answer? Hmm. Yeah. So what can I do for you? That is, give me a second, okay? I can show you a good example. Mm, Yes, I think you can see my screen. Yeah. So this example I was showing to you basically. Okay. Yeah. So here, here you can see that many of the things are 0, and when you calculated the thing that bigram probabilities of 8 words, so this came to this one like this. So this is the bigram probabilities. This means the formula we are using here, that is this one, this formula. So using this formula, we are getting this table. Okay. Any problem, anyone? So now what we are doing, that dealing with the scale of large n-gram models, that the logarithmic. Yeah. So this is the option that like if we add one, our table looks like this. Okay, this is the formula I was showing. So this is not none about the, like we are following the book of Jurassic Martin, which is the Bible of the NLP. So you can follow this book only. Yeah. So now what happens that if you do the if you calculate the probability, the probability will look like this. So for that we are just so our question was that why we are adding this v. Okay, so this one. Yes, all, yes, exactly. Yes, yes. We are adding, hmm, hmm, exactly, exactly. That's the answer. So, yes, you have, yes, exactly, that's the answer. So then there's a problem. So after that, you can see that this is the table. This figure 3.7 is the table. Okay. Before adding, before doing this calculation. Okay. So after doing this calculation, the table looks like this. Okay. Now there is something we need to see that what is happening here. So yeah. So we can compare this diagram before and after smoothing. Okay, so we have to compare this one and this table. Okay, so this table became some dirty, but we can use it. Yeah, so we have to compare this table and this table. Okay, there is a reason why I am comparing. Let's see it. This one. So the comparison is like that. So if you see that we have 3.8 here at I, it was it became 3.8 from, so from 5 it became 3.8. Okay, but this this Chinese got significant, uh, yeah. So this Chinese got significant exposure, 0.64. Okay, so basically what happens here, that this 133, you can see it here, this to Spain it was 133 and previously it was 212. Okay, and so basically what happens, what I'm trying to say, that this was 2, that one spent, this was 2 and it was 3, it came to very low number like 1.9 and 0.78. So people who were rich, this operation or like this budget, so this didn't affected the large, like the richer one. Okay, so this one Spain and two Spain was a richer guy, like this 133, because previously it has the 212. This operation didn't affected much the rich guy, but it affected the middle, the uh, mm, the middle ones. Okay, so this is what I want to say. So that's why there is something, another smoothing concept like add k smoothing came into the picture, where we are adding k with kv. Okay, so this is the thing, this is the approach. Okay, now came back to our solution that we were trying to solve this question, that is, yes, dried barriers. Yeah, so dried barriers were was calculating this many times. Okay, so this was we are trying to solve. Yeah. Mm. So basically what I have to do, that we have to find what is the vocabulary size of C2. We have to find the vocabulary size of C2. How can we find this? Find that. So basically we have to find the V. What is the vocabulary size? So we know that probability of maximum likelihood estimator, even BERRIES DRIED, which is the bigram, is given by count of dried given sorry, dried given berries. Okay, and by count of dried. Okay, so it is given that dried berries is 0.4. So it is like that 0.4 is equal to C of dried berries. Okay, and by C of dried. Okay, fine. That means C of, and also we have given the C of dried, which is 680. Hmm, okay, so C of dried is equal to 0.4 into 680 is equal to 272. Okay, now probability of add one, which is berries from dried is equal to count of dried berries plus 1 by count of dried plus b. So we know all of the thing like 0.05. Done this is this one like 0.05 plus 272 plus 1 by this thing. So you will get p as 4780. I think you get it. So you have to put it here only is equal to 272 plus 1 by 678 plus p. So if you solve it, you will get it the 4780. Fine. Yeah, this was all. Yeah. Okay, fine. Now come to our question, next question. So this is clear to all, I think. So anyone can like raise your hand or tell me if not understood. Hmm. Now the next question. Yeah. So for the next question, so we'll be seeing that we have three sentences. There is a big garden, children play in a garden, they play inside beautiful garden. Okay. Now see the question. Calculate the probability of they play in the big garden assuming a bigram language model. So how will you calculate? So this is the sentence. There is a big garden, children play in a garden, they play inside a beautiful garden. So you have to calculate they play in a big garden in bigram language. Bigram language. So this you have to calculate the probability of. Mm-hmm. Hmm. All the product of the bigrams, yes. And also before that, uh, add this one. Add the beginning of the sentence and beginning token and end token. Yeah. So this will, we can solve it by. So do you need more time? Are you solving? So I can go ahead. So this is given by like, so we'll solve it like this. So this is our beginning sentence. They play in a big garden. Okay, and this is the end of thing. Okay. So the probability of they given starting of the sentence is 1/3. Probability of play given they is 1/1. I'll say it. Let me write it down first. Yeah, I'll say it. So basically, you have to multiply all those things, and you'll get the answer. Okay. Now, what does this mean? So this means that count of starting and they. So you remember this formula, right? You remember this one. So berries dried. You remember this formula, right? So berries dried. We want to calculate the probability. So we count like dried berries. So that's what I am using here. The We want to calculate the probability of they. So that's why S they and count number of time the word they. So this is the thing. So how many times there is a end of sentence? There was a there was a beginning of sentence. This is the beginning of sentence along with they appeared, and how many times the word they appeared? Okay, so sorry, I have done some mistake. So what was our formula? So our formula was how many times? So how many times dried? So this one, this quantity. This quantity was here. So same thing we have to do this quantity here. So how many times end of the sentence, the beginning of the sentence appeared. So that's why you can see that there is a beginning of the sentence, there is a ending of the sentence. There is a beginning of the sentence, there is an ending of the sentence. Okay. So beginning of the sentence and ending of the sentence. So at the beginning of the sentence, only one time, is they. This appeared only one time. But the beginning of the sentence appeared one time, two time, three time. Am I able to like make you understand that what is happening? Okay, yeah. So that's why this is 1/3. Okay, so like this, I have calculated all this and then multiply all of them and got the answer of 1/2. Okay, yeah. So this is the thing. Now comes to the second question. Second question is, consider the same model as in question 7. Calculate the perplexity of S they play in a big garden. So we have to calculate the perplexity. So I told you what is the formula of the perplexity. Perplexity was the this word given minus 1 by n. Okay, so can you calculate it? So you have to use this one. So this 1.12. Mm. Okay, fine. So does anyone has their answer? Mm-hmm. Yes, it will be. So why it is cube root of why it is cube root? And our formula is minus 1 by n. So Bala, can you explain what is the what why you are saying 1 point? Yeah, 1.426. How? Okay. Mm-hmm. Mm. Yes, yes. Mm. Yes, exactly. So 1 by 12 into whole to the power 1 by 7. There are 12 bigrams. Yes, so that will be 7th root of 12. That's why 1.426. Mm-hmm. This is the correct answer. Thanks for answering. Yeah. Okay. So can you introduce yourself? So where are you from and like, which course are you in? Mhm. Okay. Thanks for introducing. Yeah, great to meet you. Yeah, thanks. So okay, now okay, next then move on to the next question. This one. Assume that you are using a bigram language model with add one smoothing. Yeah, calculate probability of. So this is like together. Yeah, probability of they play in a beautiful garden. So there is no you can see here that there is no ending and starting token. So we will not also use it. Okay, or we can use it. Mm. Okay. So okay, let's rephrase our question once. Um, One smoothing. So here we can find out like this probability of we are adding the starting and ending of the sentence. Okay, the garden. So basically, I have changed what I have changed here. Like I am adding the starting and the ending. Okay. So this is what. So we have to calculate the add one smoothing here. Okay. So we have seen the formula for the add one smoothing. What was the formula? Formula was adding one and the formula was probability of add one given wi minus one and wi it was wi given wi minus one. It is written like this. Yeah. Then what I do that we count the number of wi minus one wi plus one and wi minus one order three. So this is the formula for us to calculate the add-one smoothing. Okay. Now we go back to our problem that how we can calculate. So how many what is mod B here? So how many vocabulary are there? So this is one, two, so this is two, three, four, five, six, token, end of token, that is 8. Okay. But mm, okay. Hmm. Okay. So in bigram, how they are doing this? So basically, they are calculating the number of V, like number of vocabulary. How they are calculating the unique number of vocabulary. So what is mod V? So mod V, we can find it from the corpus. So 1, 2, 3, 4, 5, 6, 7, 8. So A and garden is repeated. So that's why I'm not counting again. 8, 9, 10 is repeating. Inside is not repeating. 11 is beautiful. So mod V is 11. Fine. Is it clear? So this is the thing. And also we have calculated that, yeah. So calculated this. So now, so mod P is 11. Okay. So we have to calculate the other thing. So how we can calculate? So we have to calculate before calculating this one, we have to calculate what is probability of the given beginning of the sentence. Okay. So which is, uh, it is given two times, I think. So basically, so we have already done this one. So here, this one. Okay. Okay. So here, what we have to do, that in, you remember this was, like we have to find we were trying to find the probability of sentence. So that's why we are calculating this. So what we have to do here? Here we have to add 1.